Insert in BST. How do you insert a new node into a binary search tree? Here, you have to find the appropriate location where you can insert a new node by maintaining the binary search property. So this is your task. Rule number one, whenever you are inserting, keep this in mind that the new key is always inserted as a leaf node. You'll never insert a new node in between somewhere in the binary tree. You'll always insert it as a leaf node. So what is the process for this? The process is similar to binary search, that not binary search, search in a binary search tree. So this is the process. If you have a binary search tree like this, if this is your binary search tree, you have a new element that is to be inserted. Let us say element with value x. What will you do? First, you will prepare a new node with this value. The next thing is to insert this new node at the right position in this binary search tree. So initially, you will continue the process similar to search. You will go to the root. You will see whether x is larger than this value or smaller than this value. If it is smaller, you will go to the left subtree. If larger, you will go to the right subtree. So you will do this till you reach a leaf. So whenever you reach a leaf node, what happens? You will again check whether x is smaller or larger. Then let us say this is the leaf where you reached because x was larger than this value, smaller than this value. So you reached here. From here, you will again see whether x is smaller or larger. If it is smaller, what will you do? You will create a new link here and then x will be added here. This is what you are going to do. This is how insertion is done. I'll take numbers and then show a dry run. We'll take the same tree that we considered for search, 50, 21, 74. Then we had 15, 32, 63 and 80. Let us say the new value I have to insert is 71. What will I do? I'll initially create some memory in that node. I'll add 71 as the value. After doing this, I have to insert 71. I'll check with 50. 71 is larger, so I have to go to the right subtree. I'll check with 74. 71 is smaller than 74, so I have to go to left subtree. Once I reach left subtree, the value is 63. 71 is larger than 63, so I have to create a right child. Here I'll insert 71. So this is how I'll do insertion in a binary search tree. Let us write pseudocode for this and then we'll understand time and space complexities. So in pseudocode, what all are the steps that we need? We need to start from the root. We need to continue the process similar to search. We should go and try to find a position for this. Whenever you reach a node which is not having any children, then you know this is the position where you can insert. So you check both the children. If both the children are not present, you see whether the value you want to insert is smaller or larger than that particular value. If it is smaller, add a left child and put this value. If it is larger, add a right child and put this value. This is the logic you have to put in pseudocode. So in the pseudocode, let us say you want to insert in BST. So BST insert, this is your algorithm. In BST insert, you will have a value root. So whenever you want to give any tree to a function, you will give the root. Root is the identity. Root and k. So k is the value you want to insert. So what you will have to do, you will have to create a new node and you should put value k inside, and then that k is to be inserted into the correct position. So for now, let us consider you want to create new node with value k and you are going to start this with root. So from root, what should you do? First thing, you have to check if at least there is something. If root itself is null, that means this tree has no elements. If root is null, what can you do? You can add a new node as the root of the tree. So what will you do? If root is null, what will you do? You will create a new node. Let us say you will create node, and this node will have value k. So you will add this as the root. That is the process you have to do. Otherwise, what should you do? If the value, that is the value k you're searching for, if it is lesser than whatever is present in root. If k is lesser than root pointing value, if k is lesser, what should you do? You have to check the left child. If left child is present, you have to recursively go to the left child and continue same process. If left child is not there, that is when you can add this value as a new node in the left child, right? So if left child is there, if root pointing left, if root pointing left means left child is present, in that case what should you do? You should recursively call the BST insert function. So you should call BST insert, you should recursively call on the left child, right? So you should call on root pointing left and the value to be inserted is k. So it will continue the same process whatever you are doing in root pointing left. Otherwise, else means if left child is not present, what can you do? You can add this new value as a new node in the left child. So then what should you do? Then you should have root pointing left, that is as a left child you are going to add the new value. What is your new value? Let us say you will create a new node, create node with value k and put it in the left child. What is the next thing? The same process you have to check with the right child, that is if the above condition is not hit, if it is the case that k is greater than root pointing value, whatever is the value in the root, if k is larger than that, what will you do? You will check the right child. If right child is present, that is if root pointing right. So if root pointing right means if root pointing right is true, that is if it is present, what will you do? You will recursively call BST insert in root pointing right. So root pointing right, and you will put value k. K is the value that is to be inserted. Else, that is, you know the value is larger than whatever is present in root, but root doesn't have a right child. Then what will you do? You will create a new node and put it in root pointing right. So root pointing right is equal to, so this create node function, I'm just assuming that it will create a new node. Just put value k inside it and return that node. Okay. That's why I'm not writing this function separately. There is nothing to be done in this function. So create node of k. So with value k, it will create a new node. And what should it finally do? Finally, once all these steps are done, it has to return the value of node. So return root. So why are you returning root? Finally, you should return the tree after you insert it. So what will it do? It will recursively return at whichever point you have added this. After that, from that node, it will return that particular node. In the previous recursive call, it will get fetch this and return it to the previous call. So finally, it will reach the first call, the initial call that was made. At that call, root of the tree will be returned back after making all the changes. So this is the algorithm. Let us just see this once more. BST insert, what are we doing? If the root is null, if there is nothing in the tree, you will create a new node and that is the insertion. If there is something, that means at least one node is there, one root is there, then we will check whether the value of k is lesser than or greater than whatever is the value of root. So if you want to add equal condition, you can add here only, okay? If k is less than root, then what will you do? You will go to the left child. If left child is present, you are going to recursively continue the same procedure on left child. If left child is not present, you will add this as a new node into the left child. It was not present, so you will give it a left child. If k is larger than whatever is there in the root, you will go to the right child and recursively do it in the right child. If right child is not present, then you will create a new node and make it the right child. This is the algorithm of insertion in BST, binary search tree. Next thing is, what are the time and space complexities? Coming to time complexity, what is this algorithm doing? It is starting from the root node, it is going down going down. In each step, it will go one step down. In whatever direction, it will go one step down. So maximum time it will take is the time to take from root of the node till the farthest leaf. That is the height of the tree. Maximum time possible is height of the tree. And in case of BST, what is the worst case height? Order of n. That is when the tree is a skewed tree. And what about the space complexity? Space complexity is also order of height, that is order of n. Again, same as a search algorithm, if we write an iterative algorithm for this, we can reduce this space complexity to order of 1. So for this recursive solution, time complexity is order of n, space complexity is also order of n.